Welcome to the presentation on stability of open-top cylindrical steel tanks with primary stiffening ring under wind loading. This is a study that was completed by Dr. Ozer Zeybek, myself, and Professor John Michael Rotter from the University of Edinburgh. Here is the outline of the presentation. I will first talk about the structural configuration of storage tanks, wind pressures on circular cylinders. I'll try to give you the motivation of the study, and followed by that, I'll try to talk about the developed shell ring stiffness ratio and results on the buckling behavior of cylindrical tank structures and development of design expressions, and finally, the conclusions. Now, this slide shows us some structural configuration of storage tanks, like the vertical cylindrical fixed roof tanks, vertical cylindrical floating roof steel tanks, spherical steel tanks, or elevated water tanks as such. The main controlling failure mode for these types of structures is buckling under external or internal pressure. So we see some failures of these tank structures in this slide. The function of this primary stiffening ring, or sometimes the member that's called as the top wind girder, is twofold. The stiffening ring is placed at or near the top of the tank to strengthen the tank wall and to enhance the buckling strength. The ring also plays an important role in maintaining circularity when the tank is subjected to wind loads. There are stiffness requirements for this primary stiffening ring, and the ring must have an adequate stiffness to fulfill its function. When we look into these requirements, it's usually given as a function of the minimum moment of inertia, or in other words, the second moment of area of the primary ring. So there are recommendations by Blackler, by Schmidt, by Greiner and Guggenberger, and there are also codified provisions. The wind pressure on circular cylinders varies around the circumference, and usually it's given in a series form where it's a function of L over DC or DC over L ratio. There's also an inward pressure that's produced in these type of structures, and we usually come up with this inward pressure coefficient of 0.6 if we were to use Euro codes for design. The motivation of the study is as follows. We try to develop a more rational approach for the design of the primary stiffening ring. The approach depends on the relative stiffnesses of the primary ring and the shell. The stiffnesses were derived for the harmonic loading, which is given by this expression. In here, QR of theta is the circumferential variation of the non-uniform line load considering wind pressure Q. For any single harmonic loading, closed form expressions were obtained for the radial displacement of the shell and the stiffening ring. So the couple of slides are going to focus on how we develop this ratio. So the idea here is to develop a shell ring stiffness ratio, which is the stiffness of the shell divided by the stiffness of the ring. And in order to obtain the stiffness of the shell and the stiffness of the ring, we basically derive the displacements, radial displacements of the shell due to this harmonic loading, and then the one for the ring due to the harmonic loading. And finally, we will get the ratios. So UR of ring divided by UR of shell will be the shell ring stiffness ratio that we are looking for. Again, in the following slides, I'll try to summarize how these displacements are obtained for the given loading condition. we start with the shell ring stiffness ratio, and the first thing that we are going to derive is the ring stiffness. In order to develop the ring stiffness, Vlasov's curved beam differential equations were adopted. And you see that there are 6 equations that govern the system behavior. And what we are going to do is take these 6 equations and then first start with the loading condition where we only have radial loads QR and all the other loads are equal to 0. There is only one uncoupled differential equation of equilibrium, which reads as follows. The solution of this differential equation gives us the bending moment in the ring about a transverse axis, given as follows. After this point, the force deformation expression needs to be used to obtain the radial displacement U sub r. So after using these 2 equations together, the radial displacement of the ring can be developed as follows as a function of cosine m theta for any given harmonic m. In a similar way, we would like to derive the shell stiffness for this given loading condition. For this purpose, the non-symmetrical radial load can be transformed into a tangential shear loading called nx theta at the top edge of the shell, considering an edge string treatment which was proposed by Kelladine in 1983. To derive the shell stiffness, the membrane theory of shells was used. In the membrane theory of shells, the equilibrium equations are represented as follows. So those 3 equilibrium equations were used together with the displacements and the strain displacement relationships which are given in these expressions. Detailed derivations are indicated in the paper, and considering appropriate boundary conditions, the radial displacement can be found at the top of the shell, where x is equal to L as follows. So after this step, we are now ready to compute the shell ring stiffness ratio because we have already obtained the displacements of the ring and the displacements of the shell. So finally, the shell ring stiffness ratio can be represented as follows, which depends upon many geometrical properties, parameters such as the radius of the cylindrical shell and ring, the thickness of the shell, the second moment of area normal to the plane of the ring, the Fourier harmonic M, Poisson's ratio, and the height of the tank shell. Now, this stiffness ratio was used to explore the buckling behavior of cylindrical tank structures. So a finite element parametric study was conducted to develop a practical limit for design of primary stiffening ring. This is a finite element parametric study which employed shell elements, as you see in the slide, and the parameters were the L over DC ratio, varying between 0.25 and 1, R over T ratios varying between 500 to 2500, and 30 different primary stiffening ring geometries. The results are as follows. First, an assessment of each harmonic wind loading was done. The effect of each harmonic of loading recommended by the European norm was investigated separately. A unit pressure was applied at the stagnation point, and all harmonic coefficients were chosen as 1. The buckling pressures, Q critical LBA, for any harmonic was normalized by the classical pressure that causes buckling, the Donnell's expression, which is given here as Q critical, D. The results indicate that there is a clear trend. Okay? The stiffness ratio, or the inverse of the stiffness ratio, captures the trend quite clearly, that as the inverse of the stiffness ratio increases, as we go from more flexible rings to more stiff rings, we would have an increase in the buckling capacity. Now, afterwards, an LBA for cylindrical steel tanks with primary stiffening ring under wind loading was conducted. Here, many M values were combined, many harmonics were combined, and it's clear that for different L over DC ratios, the grouping according to the stiffness ratio gives a very clear trend for the behavior, for the buckling behavior. And the buckling behavior can be divided into three regions, region 1, region 2, and region 3, which can be expressed mathematically. So the nice thing here is that mathematical expressions can be developed to derive these regions. In addition, a new limit for the moment of inertia of the primary ring can also be developed. So the proposed value is here, and the older proposed values are also indicated in this slide. So finally, we were able to develop expressions for these three regions for different L over DC ratios, which can be readily adopted in design. Also, a minimum second moment of area of the cross-section is also proposed, which can be written as follows. Now, in conclusions, this paper has presented new stiffness requirements of the primary stiffening ring at the top of the wall of a ground-supported cylindrical tank under wind loading. The buckling resistance of the cylindrical steel storage tanks with top stiffening ring under wind loading that varies along the circumference is investigated considering internal suction using finite element analysis. The changes in the buckling capacity are studied in light of the proposed stiffness ratio that represents the ratio of stiffnesses of the shell and the primary stiffening ring for a particular harmonic of wind loading. So this is the stiffness ratio that we end up with. The results reveal that the changes in the buckling capacity are closely related to the shell ring stiffness ratio, and the rational procedure to determine the minimum second moment of area of the cross-section was developed for the primary stiffening ring, considering buckling capacity changes in the tank structures. Thank you all for your attention. This is the end of my presentation.